today. So great to be here. Great to tell you a little bit about the research that we're doing in Edinburgh about using the eye to uncover early indicators of Parkinson's and other neurodegenerative diseases. And I can move my slides. Here we go. So just briefly, some objectives today is obviously I'm here to tell you a little bit about our research, give you some background to this, why we're doing it, what we've done in the past, what we're planning to do in the future, and then really interested to hear your reactions to that, what you think about it, and yeah, get your take on what we're trying to achieve. David mentioned some of this, so yeah, just to give you a little bit of background to me. So my background was in physics originally, and then for the last more than 20 years, I've been working in clinical research at the Clinical Research Facility in Edinburgh. I'm also part of the Edinburgh Imaging Group, where we use medical imaging techniques in clinical research to uncover things inside the body and brain. And I've got a specialty in retinal imaging. And then as part of the Centre for Clinical Brain Sciences at the University of Edinburgh, lead my own research programme. So a lot of what I'm going to talk about is the application of imaging and analysing those images. So that's really my area of expertise. And then through these different centres and groups, there's a real mix of people coming together, scientists, ophthalmologists, neurologists, lots of different people working together. So I'm part of a larger team of people. We all bring our expertise into the mix to achieve our research programs. So just some of the sort of background context, you might have seen headlines like these appearing in the news. These are some I've grabbed over the years in the field of neurodegeneration. People talking about eye tests and using eye exams to detect Parkinson's or Alzheimer's, dementia. I've got one there about Moorfields Eye Hospital in London. They linked with Google a few years back, and they actually hit the news for the wrong reasons in terms of problems with data and people's data being used kind of inappropriately. So there's kind of a lot of things that might hit the news or do hit the news around using the eye to study and look at and detect neurodegenerative diseases. So you might have seen similar headlines appearing on websites or in newspapers. So I'm going to give you the background as to why, how these news stories sort of come about. Why the eye, basically, and from this. This image is in all its gory detail with the representation of the brain with no skull. You can see how interlinked the eyeballs are to the brain. And in fact, when the human body starts to develop and grow as a fetus, the eye emerges as an outcrop from the developing brain. So the eye shares a blood supply, it shares nerve tissue with the brain. So potentially it's a really kind of interesting window into what's happening in the brain. And in particular, we're interested in the retina, so the back of your eye, the light sensitive tissue at the back of the eye that when light enters the pupil, it hits the retina, that light is converted into signals that go back into the visual processing sections of the brain, and that's how we see, that's how we interpret the world around us through the connection between the retina and the brain. But it's a part of the human body that we can look inside really easily, because I would imagine that I can sort of see from some of the screens that lots of you are wearing glasses. There's a good chance you've been to get an eye test recently. The optician will have looked inside the back of your eye, would have checked the health of your retina, would have checked the front of your eye for maybe cataracts. They would have taken a picture of the back of your eye, and through the kind of quite easy imaging, we can see inside the human body, and we can see blood vessels and nerve tissue at the back of the eye that are connected to the brain. And this is the crux of what we're interested in is that we think that what happens at the back of the eye is a really good marker for what's happening in less accessible parts of the brain, which are quite difficult to study inside the human body. And just to kind of give you an idea of the sort of scale, the sort of size, that if you go for an MRI or a CT scan, the sort of level of detail is about millimeters. You know, if you imagine looking at a ruler, you see the scale for a millimeter, that's the kind of level of detail you can see in a CT or an MRI scan. But when we look inside the retina, we're essentially using microscopes to look inside the back of the eye, and we can see things down to microns, so a 1,000 times greater level of detail. So it's a smaller piece of tissue than the brain, but we can examine it to a greater level of detail than we can do with brain scans. This is the most common type of image that is collected. This is with a device called a fundus camera. So when you go for an eye test, the optician is always going to take one of these because they get paid to do that by the NHS as part of a routine eye exam. And it's technology that's been around for 40, 50, 60 years. Digital cameras appeared in about 2006. In fact, there was a big investment by the Scottish Government to put a digital camera in every high street optician around about 2006. So the technology's been there for quite a long time. It gives a really nice picture of what the back of your eye looks like. You can see the little small blood vessels there. You can see that bright disc in the middle. That's called the optic nerve head. That's where the nerve tissue leaves the eye and makes its way back to the brain. And the size of these blood vessels, they're in tens or hundreds of microns. They're not too dissimilar to the size of a thickness of a human hair. So really small blood vessels that we can see inside the human body quite easily, quite routinely. And then a lot of what we've done research-wise has been to say, well, can we detect and analyze these? And can we use things that we can measure from these images to tell us something about microvascular health? And potentially microvascular health in the retina is a really good marker for microvascular health in the brain that we can't quite see with MRI or CT scanning. We can see signs of injury in the brain with MRI and CT, but we can't actually see the really small blood vessels. And here, the back of the eye, we can see them really easily. We can process them with computers, and we can measure properties that we think characterize the health or state of the microvasculature. Then the other sort of common technique that you might find on the high street is optical coherence tomography. Definitely find that in eye hospitals. What that's doing is that's looking at the different layers at the back of the eye. So this is a cross section. So this is you imagine the red line there at the top is the surface of the retina. And then what we're doing is we're looking through the different layers at the back of the eye, the different layers of cellular layers and nerve tissue and things that are going on in the retina that are the anatomical structure. And we can see that with this technique called OCT. Now in Parkinson's, this is a paper from about 2 or 3 years ago, where a colleague of mine, Siegfried, and his research group, they looked in the UK Biobank, which some of you might have contributed data to. About 15, 20 years ago, UK Biobank collected retinal images, OCT, and fundus camera images from about just under 100,000 people. And then a couple of years ago, Siegfried and colleagues, they looked through that data to find people who had a diagnosis of Parkinson's disease. And then they analyzed those OCT images, and then they looked at the different layers at the back of the eye. And then in Parkinson's, as you guys are going to know, that there's a premature dying of neurons in the brain, and in particular, dopamine-producing ones. And when you lose those dopamine-producing neurons, you're leading to things like tremors and muscle stiffness and other some of the sort of symptoms that I don't need to tell you guys about. You're going to know this stuff much better than me. The key thing that Siegfried found and team found is that where the dopamine producing neurons are in the retina, he was seeing a loss of nerve tissue. So by looking in the back of the eye, he was seeing a loss of nerve tissue that is connected with Parkinson's that was happening in people with Parkinson's. So this is kind of the sort of, at the time, the biggest study of its time to say, if you look in the retina, you see neurodegeneration, you see loss of nerve tissue, and it's happening in people with Parkinson's. Now, there's another way to image the retina. You might have heard of a company called Optos. They were originally a Scottish-based company. They're based just outside of Dunfermline. They've been around for about 20 odd years. They came up with this really clever way of using lasers and mirrors to scan the back of the eye. About 10 years ago, they've been a huge success. About 10 years ago, they got bought over by Nikon. So they're now part of the large Nikon group. They're still based just outside Dunfermline in their headquarters there. They've got some really interesting technology, lasers, mirrors. You get a much bigger view of the retina of the back of the eye than you would do with the normal fundus camera. It's kind of really interesting for us as researchers to then study more about the blood vessels that we can see in the retina. And then we sort of worked out how we could take what we know how to do with the fundus cameras, apply that to the Optos images, and do lots of measurements of blood vessels and the health of blood vessels at the back of the eye. And then working with some people at Duke University in the States. This is from a couple of years ago. In Duke University, they were using the Optos device to image people with Parkinson's, and then we helped them analyze those images, and we found that there was abnormalities in the patterns of blood vessels. So it looked like there was essentially the blood vessels looked a little bit unhealthy. It looked like they'd deviated away from kind of a normal, healthy arrangement of blood vessels into something that looks a little bit dysfunctional. So this is sort of thinking, well, we know the nerve tissue is degenerating, and now we think that the blood vessels are showing signs of dysfunction, and that these two things are linked, that there's some microvascular dysfunction as well as degeneration happening in there, and that these things are interlinked. But the key thing is, in this study, we were looking at people with Parkinson's, and in the UK Biobank study, Siegfried and colleague were looking at people with Parkinson's, and that's really interesting from a research point of view to know that there are things happening in the retina in this particular disease, but when do they happen? When do they start to occur? And how might we use that information in some way? So that's why the eye. The eye is giving us a really interesting window into microvascular health, nerve tissue degeneration, and we can do this from quite simple, straightforward eye scanning. In fact, eye scanning that actually happens every time you go for an eye test, which is then the sort of what a big focus for us at University of Edinburgh has been to say, well, if this is happening on the high street and it's happening all across Scotland, and can we get to this data? Can we use this data in research? If it's been routinely collected, then can we find a way to access it for research? And if we can, then fundus camera images like this orange image are taken at every eye test, and we can analyze blood vessels at the back of the eye. OCTs are not taken routinely. You can pay a little bit extra money and an optician will give you one of these scans. But actually, from the UK Biobank, we can learn using things like artificial intelligence techniques. We can learn the relationship between the OCT and the fundus image, and we can actually work out how to get nerve tissue measurements from just the plain old fundus camera image. And we can also do a thing called pallor. Pallor looks at the brightness or paleness of the optic nerve head. And if you lose some nerve tissue in the back of your eye, then the appearance of that's going to get paler. So actually, there's quite an interesting measurement. Just by looking at how pale or not the optic nerve head is, we can get another really interesting marker of change in nerve tissue. Now, I wanted to just bring this slide up because a lot of what we do involves artificial intelligence. A lot of what we do when we're analyzing blood vessels or analyzing nerve tissue, measuring things from images over the last 10 years or so, artificial intelligence has completely revolutionized this in terms of our ability to measure things, learn the relationship between things, do things at a level of accuracy that couldn't have been done before. But I think artificial intelligence, we use that term, and the media use that term. Everybody uses that term. It's a bit of a catch-all term, when in fact, a lot of what we're doing is machine learning. And more specifically, a lot of what we do when we analyze these images is actually deep learning. It's a subset of machine learning. And and generative AI, which is all your ChatGPT and Microsoft Copilot and things like that. That's another subset again. So I just think that in terms of the language that we're using, we're maybe using artificial intelligence as a catch-all, when actually we should be maybe more specific about what type of processing we're doing. That's maybe for a piece of information, maybe for future discussion, is should we be actually explaining ourselves a little bit better when we talk about artificial intelligence rather than just using it as a buzz term. But back to the high street optician. So there are, I've got a slide with the numbers of opticians' practices in Scotland and the number of eye exams. Can we get to this data? If we can work, we know how to work with the data, but can we get to the data? Now, some of you might have been involved in research where you get asked if you'd like to take part, you get given an information sheet, you read the information sheet and you sign on the dotted line and you say, yes, I'm happy to be involved in research. We can't do this here because we can't go around everybody in Scotland that's gone for an eye test and say, can we use your images, sign on the dotted line? That would just, that would be a huge logistical challenge to undertake. What we've done instead then, in order to do this, is we've created this project called Scoon. Here's the detail, actually. Yeah, so here we go. Here's 17,000 optometrists, 900 high street practices, over 2 million eye exams performed annually on the high street. So logistically, we can't really go around and ask everybody if we can use their eye data, because that would take us from now until we all retire and stop doing research. But can we find a way to bring all this data together? And we've done this, actually. We've already brought together this number of images from this many patients, this many practices. That's taken us a couple of years to do. And the other thing we've been able to do is then link that to other routinely collected information. So if you go to a hospital and you get a code for a diagnosis, or you have an operation, or something happens to you, every time you touch the NHS, your CHI number, your Community Health Index number, records that. And that also happens for an eye exam. So when you get an eye exam, your CHI number is used to record you, and every time you touch the hospital system, your CHI number is used, and then we can link all that together so that if you've been for an eye exam, then we can also look to see what other points of contact you've had with the NHS. How are we allowed to do this is going to be your question. If we're not going around asking everybody if we're allowed to use their images and their other hospital information, how come we've been allowed to do this? It's a really important question. Is rather than going to an ethics committee and going through the process of saying, this is what we want to do, and this is the information we're going to give to the patients, and this is the signatures that we're going to collect, and this is how we use the data, we're not doing that. We've had to go through a different process. We've had to go to this public benefit and privacy panel. So imagine it's like a really big ethics committee who sit and specifically look at people's requests to use routinely collected data. So an eye test is a routine thing. You're going into hospital to see a doctor, that's a routine thing. If we want to use that data, then we have to convince these people that we can do that safely, securely, and keep people's data protected. So this was a huge part of the Scoon project. In order to be able to do the Scoon project, we had to convince this panel that what we were doing was in the public's benefit, and we could do it securely and privately and keep everything safe and secure. And that's what we did. So when we collect any data, it goes into what's called a safe haven, which is a really secure, protected environment. It's run by Public Health Scotland through their ERIG team. Any data that's in there, we link it with a CHI number, but then it's anonymized and people are just represented by a number. So all this data gets collected into the safe haven. So we can't identify individuals from this. We can't tell who anybody is. We've just got data that's linked together. But then we're allowed to use this data in a research environment that's all secure and overseen by Public Health Scotland. So what we're planning to do around Parkinson's, well, if we go into the data we've already collected through Scoon, we've got 429 people with a diagnostic code for Parkinson's, and there's 4,000 images, or just over 4,000 images. And in fact, about 3,000 of those images are predating their diagnosis. So people have been going for eye tests, and then they'll have a diagnosis for Parkinson's, or it could be another neurodegenerative condition. And then we can look for the images that are before the diagnosis and images that are after diagnosis. And then we can do something really quite unique, is that we can look at how the retina is changing before someone's disease becomes so significant and prominent that they've gone to the doctor and they've gone through all that process of being examined and tested and being given that diagnosis. And it's not something anyone's been able to do before, because the UK Biobank was just looking at people with a diagnosis. When we worked with Duke University, that was looking at people who had a diagnosis. This is the first time we've been able to go into this data and say, well, what happens to someone before they end up with their diagnosis? And then we can do our analysis. We can look at the fundus camera images that are taken at every eye test. We can examine the blood vessel health. We can examine nerve tissue health. We can look at optic nerve head. And we can look to see what's changing, what sorts of signs of disease start to appear in that run up to diagnosis. And we think that people with Parkinson's will have difference in their retinas in the months and years prior to their diagnosis compared to other people of a similar age. Well, what retinal features are most discriminatory? What are the key ones here? Is it the blood vessels? Is it the nerve tissue? Do the blood vessels change before the nerve tissue? Do things change at the same time? Is it the nerve tissue and then the blood vessels? We can start to answer questions about that early prodromal, preclinical stage of Parkinson's that no one's really been able to do before. And when do these retinal signs start to appear? So then why do it? Why? Well, this is what we think. And this is, I think, the bit where it was really key to get feedback on this, because we think we can uncover brain changes associated with the early stages of Parkinson's through the retina. And we could gain new insights into the early progression of disease. And we can do this from routinely collected healthcare data. So we don't need to go and do something new in terms of recruiting people into study. We can do this with data that's already been collected. And why? Well, it could help with earlier detection. You could imagine maybe a scenario in the next couple of years where you could alert that a person needs to be monitored or requires additional investigation because their retina is changing in such a way that it suggests Parkinson's. If you find signs of Parkinson's earlier, could that then help with better management of someone's symptoms to improve their quality of life for longer? And with an eye on the future, as and when future therapies start to appear and are there, maybe that's further into the future. But could the retina, could imaging the eye be a way to find that most effective time to give someone a new therapy to slow or stop progression of disease? So that's what we think we can do through analyzing these types of images, is potentially add these kind of these positive things to the sort of detection and management of disease. This is where we do lots of our research. It's in the building. We would have been near this had we met in person today. So this is the Institute for Regeneration and Repair. It's the South building where we have our EyeLab, where we have our collection of scientists who sit together and work out how to do this analysis. We meet with ophthalmologists and neurologists to discuss these projects, and where we run from here and from the Usher Institute, which is a little bit further up the hill at Little France, where we run the project to go and collect data from the high street. And this is the team. I'm talking to you today, but there's lots of people that do lots of this stuff. Key has been Claire, who looks at the data governance, who's been through the entire process of securing the permission to be able to go and do this type of project. And then lots of people who are involved in collecting that data and then working out how to do the analysis. And I just wanted to finish this. My last slide is just my email address is there. We would love to be able to engage with this group. We would love to be able to get people's feedback, reaction. If people have got any questions or comments or just want to know a little bit more about what we're doing, then open to having those discussions. Email address is there, and David obviously has my contact details as well. So I think it's just an opportunity to tell you about what we're trying to do and to gauge your feedback on that. I was chatting to David earlier in the week. We are currently applying to Parkinson's UK for money to do lots of the things we want to do. We need the research funding to enable us to undertake the work, and being able to engage with this group would be a really strength of future projects going forward. So thank you very much for your time today.
Thanks, Tom. I'm going to stop the recording now, and we'll just have a brief